Welcome to episode 2. This is cool stuff my friends don't care about.
John Mark, can you shut up? I'm trying to make a TikTok.
This episode is all about light and the delayed choice quantum eraser.
Okay, no it's not. I wasn't smart enough to figure it out, and apparently that experiment has some haters. But we're still going to talk about light, how weird it is, and how our bodies turn photons into brain signals. Rainbows might have given us our first clue that there was more to light than meets the eye. Our entire existence is shaped by light. It's one of the 4 fundamental building blocks of our universe. As we sit here, we are surrounded by it. Just like we would be surrounded by water if we jumped into a pool, photons are whizzing all around us. Radio waves from Wi-Fi and cell phones, visible light from light bulbs and computer screens, the stovetop gives off infrared light, the microwave blasts your food with microwaves, and the sun is hitting us with all sorts of light. We are awash in a pool of light beams. And there are hints of this hidden substance: the warmth of the sun, the color of a sunset, or the magic of an incoming text message. But most of our interactions with light are so common, we never imagine how strange it really is. Let's start with its speed. Light travels about 670 million miles per hour, but it always travels that fast, which is strange. Think about it. Let's say I can throw a baseball 50 miles per hour, and you put me in a car traveling 50 miles per hour. How fast can I pitch the ball? You add it up, 100 miles per hour. That makes intuitive sense. But light, it doesn't work that way.
But the weird thing about light is because the speed of light is always the same, it doesn't add in that way. So if you're piling along in a train and you shine a flashlight from the train and you measure the speed the light comes out of the flashlight at, it comes out at exactly the same speed as if you weren't in the train in the first place. So speeds don't add. The speed of light, whoever measures it, however you produce the light, always comes out to the same value, C.
So light always goes the same speed, no matter how fast you're going. And not to say it's not weird, but this next experiment, this one blows my mind. Because it's not just strange. On a quantum level, light behaves completely outside the boundaries of our comprehension. Check it out.
First need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is, matter, through 2 slits, we get this, 2 bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through 2 slits, we should get, like the marbles, 2 bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this.
Okay, I don't know if I'll do this any justice, but I'm going to try. It's true that photons act like tiny balls of light, but it's not just that. Photons also have this God-given ability to exist in all of their possible locations at the same time. And I'm not saying it could be in 3 places and we just don't know where it is. I'm saying it is in all 3 places, all at once, until we measure it, and then it's just in one place. Now, apparently it's supposed to really not make sense, but in all of this, I can see God in it. The nature of light is astonishing, and when I learn about these things, I have an entirely new appreciation for the God that I'm praying with. The last thing that we should cover, if we are surrounded by light, why don't we see the light beams, like when we watch rainfall? Part of it is because we only see visible light, and part of it is because photons are so tiny. And then part of the answer is because we only see light beams that are reflected by objects and captured by our eye. And that is a fascinating thing to cover as we close.
In rods, the photopigment is called rhodopsin. The 7 transmembrane domains of the protein portion of the molecule, called opsin, traverse the membrane bilayer. The opsin forms a pocket in which the light-absorbing portion of the photopigment, a molecule called retinal, resides. The photopigments in the rods and the 3 types of cones differ in the protein portion of the molecule, which tunes retinal to absorb specific wavelengths of light. Here, retinal is in a conformation called 11 cis, with cis referring to 2 hydrogen atoms being on the same side of an important double bond. When retinal absorbs a photon of light, a component of this double bond breaks, allowing free rotation about the bond. This change in retinal to an all-trans form triggers a series of alterations in the opsin component of the molecule. The changes in rhodopsin lead to a cascade of events in the cell. The next component in the cascade is a trimeric G protein called transducin, which in its inactive state is bound to GDP. The altered rhodopsin molecule activates transducin, allowing it to exchange its GDP for GTP. The alpha subunit of transducin then activates a phosphodiesterase in the disc membrane. Phosphodiesterase hydrolyzes cyclic GMP, thus lowering the concentration of cyclic GMP throughout the outer segment. As the concentration of cyclic GMP falls, this molecule no longer binds to and holds open ion channels in the surface of the outer segment membrane. Let's compare the action of the ion channels in the light and in the dark. In the dark, the ion channels are open. The influx of the positively charged sodium and calcium ions has a depolarizing effect on the cell. The inward current is opposed by positively charged potassium ions flowing out through potassium channels, a hyperpolarizing influence. The combined result of these ion flows, however, is the depolarization of photoreceptors in the dark.